All right, welcome back to part two. So last time you were trying to solve this problem, right? So you were trying to solve it assuming that lambda is equal to 4 over 3. And if you happen to solve it, here's the solution. You will see that given lambda as 4 over 3, you would find x star as 1/3 and 2/3, which when you add them together, when you add them 1/3 plus 2/3, is equal to 1. You see how the constraint is now satisfied. So at lambda equals to 4/3, simultaneously the constraint is satisfied and you're finding the solution that minimizes the function, right? So this is the idea that when you have constraints and you have these Lagrange multipliers, the larger the Lagrange multiplier, the more you are kind of taking the constraint into account, but not too much. You are trying to find this like fine balance. And from here, you can see that finding lambda is kind of a pain. Do you want to just keep testing different lambda values until you get it right? And that would not be like really good because you need to get lucky to find lambda, right? So so we this is why an alternative method is invented to solve this. Okay, so let's say we have the general form. This is the general form I told you about. If you can put your function to look like this, then we can also write it this way. You have this, remember, H are the equality constraints. So basically, H1 times lambda 1, H2 times lambda 2. Every constraint you have will give you a distinct Lagrange multiplier, right? So lambdas are going to be associated with equality constraints, right? Equality H, right? These are equality constraints. Now, gamma, so lambda, gamma are going to be associated with inequality constraints. So every single distinct inequality constraint is going to have a gamma value. Now, this implies that we have a lot of lambda and gamma values that could be complicated to find. And what are you going to do? Just try every possible lambda and gamma value? Well, that would not be the best way to do it. So this is why the KKT condition was essentially discovered to help us find these values. The KKT conditions are a guide that give us like conditions that has to be met. And if these conditions are met, we found the optimal solution. So the KKT condition has four conditions. And the name of these are called stationarity, primal feasibility, dual feasibility, and complementary slackness. You will have to memorize these four conditions. The KKT condition says that the optimum solution, basically, when you take the derivative with respect to x, has to equal to 0. That is called a stationary condition. And this makes sense because it's the same thing as when we are solving closed form solutions, right? That's the whole point. And when you're finding a minimum, obviously the optimum point is the point where the derivative is equal to 0. After that, we have primal feasibility. Primal feasibility is basically saying that all the constraints has to be satisfied. All the equality constraints has to be satisfied. All the inequality constraint has to be satisfied. So these two conditions are saying that when you have an optimal solution, these has to be met. Okay. The third one, dual feasibility, is saying that the gamma values associated with the inequality constraints always are greater than 0, or non-negative, 0 or greater than 0. And the very last one is called a complementary slackness. And it's saying that if at the optimal solution, gamma times G1 has to equal to 0. Gamma 2 times G2 has to, every single one of these at the optimal solution will disappear, implying that this term kind of disappears. That's what it's saying. So that is the complementary slackness. So using these four conditions, it basically helped to guide us towards the optimal solution. Now, at a first glance, it might not be obvious how we can use these four conditions to guide us. But let's look at a quick example. All right. Let's now try to solve that same problem we have been solving, but this time with a KKT condition. Okay. We don't know what lambda is, right? So this remember it was x1, x2 equal to 1, right? So this right here is the problem that we have. And now if we convert it into a Lagrangian, it looks something like this. Okay, now let's use the stationarity condition. Stationarity condition says that if we just take the derivative with respect to x1, x2, they should equal to 0. So if we take the derivative with respect to x1, this goes here, this cross out, and then this cross out is just equal to lambda. So you will see that if you take derivative with respect to x1, and you'll get this with respect to x2, and we're going to set both of them to 0 because that's the stationarity condition. Now let's add another condition, which is the primal feasibility. The primal feasibility, it's saying that x1 plus x2 is equal to 1. So here's x1 times x2 and no lambda is equal to 1. So essentially, we can combine the three conditions. We have the first condition from stationarity and the second condition from primal. And now this becomes a problem that looks like ax equals to y. And you can solve, we've learned many ways to solve this previously. It could be x equals to y. You can multiply a transpose, and then x is equal to a transpose a inverse a transpose y. So you can solve it this way if a is not invertible. But if a is invertible, then that's even easier. Then x is simply equal to a inverse y. So depending on whether x is inverse, you can also solve this with I guess gradient descent. You can solve it using this approach. There's another approach you guys probably learned called the REF in linear algebra. So you can solve this many ways. And once you solve this, then the problem is solved. The optimum solution for x1 is 1/3, 2/3, and 4/3. And this was the solution. Remember, 1/3 plus 2/3 is equal to 1. So it's dissatisfied. And lambda star is equal to 4/3, as same as the previous example we've done. So this is an example of how you can solve it. Now, this is a simple example where you can formulate the problem into a linear algebra method. However, you don't always get to do this. Like we got lucky and we can formulate it this way. Other times you have to like use your logic to kind of logically figure it out. All right, so let's pause the video again, see if you can use the same idea and try to solve this one. Okay, pause the video. I'm going to move on. The solution is right here, right, for that previous one. Hopefully you were able to get it. All right, so next, so far we've only looked at equality constraints. Let's now look at inequality constraints. Let's add that in as well. So we're making the situation a bit more complicated. So here's the function, here's the equality constraint, and it's saying that x has to be less than 0. So that's the inequality constraint. So equality, inequality. Okay. Now, based on the Lagrange multiplier theory, we basically combine the equality, add the equality and the inequality constraint, put them together to create this thing called the Lagrangian. So we now have the Lagrangian. And now let's follow through the conditions. Well, there's the stationary condition, which says that if we take the derivative with respect to x, then the result should equal to 0. Right? So the derivative should be 0. And now we have also primal feasibility, which says that these two has to be satisfied. So that's primal feasibility. And now we have dual feasibility, which says that the gamma here has to be non-negative. The last one is complementary slackness, it's saying that this also has to be true. Basically, when you multiply them together at the optimal solution, that's supposed to be zero. Okay, so let's see how we can solve this. This is more complicated than the previous one. With the equality constraint, we often can get lucky and get into a form that looks like this. However, with inequality constraint, the situations are much more tricky in a sense that, okay, let's follow through the logic, right? So we just looked at this problem and let's follow through this. We know that from the primal feasibility, this is true. This has to be true. If this has to be true, this implies that the solution could be this. So x plus 1 times x minus 2. You just kind of like factor them out. This has to equal to 0. So the solution is either negative 1 or 2. X star is equal to one of these. Well, after that, we look at another solution. The solution, the constraint says that x has to be less than 0. Well, if that's the case, then it can't be 2. So now we know exactly what x star is based on these four conditions that was given to us, right? Well, and then if we know that x star is negative 1, so therefore if x star is equal to negative 1, well, we know that this times this has to equal to 0 from the complementary slackness. Okay. Now, if this times that has to equal to 0, then gamma has to equal to 0. And this basically allows us to find the gamma, find the x star. And lastly, if we know gamma and we know x, we can now solve for lambda as well. So we can basically solve for everything here. So this is an example of applying inequality constraint. Inequality constraint, notice, we were not able to create this matrix, like this nice matrix, and solve it. Inequality constraint requires you to do a lot more reasoning. Okay. Now, inequality constraints are special because they could be either active or inactive. What does that mean? Well, here's an example of inactive. So let's say we have a problem that looks like this, right? So there's no equality. We only have an inequality constraint. And the Lagrangian looks something like this, right? So x less than 1 implies x minus 1 less equal to 0. So we have to set it into the standard form. And this x minus 1 is right here. Okay, so this right here is a Lagrangian, and now we follow through the same KKT condition, which is saying that, well, if we take the derivative, it should equal to 0. So there's the derivative. Primal feasibility says that this has to be satisfied. Dual feasibility says that gamma has to be greater than or equal to 0. And complementary slackness says that when you multiply gamma and the inequality constraint together, they should be equal to 0. Now, let's follow this logic again. How do we use these four conditions to essentially solve the problem? Well, notice that if we ignore the constraint, let's first ignore this constraint. Okay? The constraint, let's pretend it's not there. Then the minimum of this, when we set the derivative to 0, so if we don't have this constraint, we take the derivative of 2x plus 1, right? This is all we have. This gives us 4x, and saying that the solution is 0. So it's saying that if we don't have this constraint, the solution is equal to this 0. And guess what? What's the constraint says? The constraint says that x has to be less than 1. But the solution is already less than 1. This implies that this constraint is not being used. Hence, inactive. This is an inactive constraint because our optimal solution is within the constraint anyways, right? So we could have just ignored this constraint. And when we can ignore constraints, that's when the constraint is inactive, that you will still get the same solution because the optimal solution is already within the area of constraint. Okay. So that is inactive. However, like other times, then it will be active, right? So in this previous example, this is the function. So this is the function. We can see the solution is equal to 0. So if our constraint is x less than 1, so it's saying that the solution has to be somewhere in here. And it turns out that solution is 0, therefore everything's great. However, what would happen if we change the constraint and saying that the constraint has to be greater than or equal to 1, right? So now it's over here. Well, in that case, the optimal solution 0 is no longer in the region of feasibility, right? This is in an infeasible region, and this is the feasible region. We want to be somewhere in this area. Okay. In those cases, if x the constraint changed to x greater than 1, in that case, this will be considered an active constraint, becomes active. Now, when obviously when it's inactive, we can just ignore it. That seems to be pretty easy, right? When it's inactive, you don't even need it there. But guess what? When you have active constraints, the problem becomes even easier because active constraints, right? If the solution has to be in this region, well, and you're trying to find a minimum, it's very obvious that the minimum is the point of intersection. In fact, that's always the case, right? So this implies that if we want x to be greater than or equal to 1 at with active constraints, then x is simply equal to 1. So active constraints convert inequality into equality. All right, so active constraints is also very useful. Either you have inactive or active constraints. So for active constraints, the solution is simply pushed to the very edge of the boundary, which is right here, right? So that's where the solution is. So for active constraints, then I mean that's the key. That's what you need to know. So basically, whenever you have inequality constraints, you want to check basically the different cases. Is this active constraint or is this inactive constraint? And then you can either get the exact solution or you could ignore it. So either way is actually pretty good. So I think this is the same slide. It's basically saying active constraint pushes the solution to the boundary. Okay. Now, once we have a constraint optimization problem and we convert it into a Lagrangian, a common question is can we just basically run gradient descent on the Lagrangian? Right? And the answer is no. No, you can't just do that. You need to solve the Lagrangian using a KKT condition because the Lagrangian is not meant to be solved with gradient descent, and you will have to essentially massage the equation quite a bit. So, and the reason is because let's say you're trying to minimize this, right? You're trying to find an x that minimize this. Well, what if you got an x as a negative value here? Well, you can make this as negative as possible to minimize it. So you can just keep setting x to be minus 1 million, right? And then you just keep making it smaller until this reaches negative infinity, which is the smallest possible one. So notice how if you run gradient descent, x would just become smaller and smaller and smaller. Or this value here would just become smaller and smaller and smaller and smaller. So you're not really trying to satisfy the constraint when you run gradient descent. Instead, you will need to massage the equation. So for example, this equation would be rewritten into this equation. Notice the difference. Over here, I put a square, implying that the only way to minimize this is if this is equal to 0, which is what you want, right? We want an x squared minus x equal to 0. So therefore, if you put a square here, then we can satisfy the equality constraint. And over here, if we put a value on x, basically saying that if it's a positive value, then we ignore it. Nope. If it's a positive value, then we minimize it. A negative value, we ignore it. So, which is the case here, right? So this, well, anyways, so you can massage it this way, but I don't recommend it because this is very difficult to solve with gradient descent. Even if you run this with make this adjustment and run it with gradient descent, you're probably not going to get the solution you're looking for. I've tried this many times. Here's an example. Like I actually try to minimize this running gradient descent. And in the very end, remember x is supposed to be less than x is less than 0, right? Was that it? Yeah, x is less than 0. So remember x is supposed to be less than 0. However, even when you run gradient descent a lot, notice that x is not equal to 0 and h is supposed to be equal to 0 and it's still not. So inequality constraints using gradient descent is not the way to go. All right, so when you have a constraint optimization, you want to try to find a closed form solution, and if you can't find it, then you really got to do a lot of engineering to massage the solutions. Okay? So this is why there's an entire course essentially dedicated to constraint optimization problems, right? But this is not a constraint optimization problem. Normally, you will need to learn like 20 different optimization techniques for different situations. But for our class and our purpose, the key takeaway is for you to just know that constraint optimizations exist. They exist. And you know what they look like, and you need to understand the notation. What does this notation mean? Well, it's saying this is the equality, this is the inequality, and you need to understand that notation. And then these are the type of problem you need to realize can be solved by the 4 KKT conditions. The KKT conditions, if you get lucky, is easy to solve. If you didn't get lucky, then you kind of have to logically uh, um, trudge your way through the solution. You will need, for our class purpose, you need to know the KKT condition, and you need to basically know how to use them for at least the simpler cases, right? In the real world problems, luckily, that Python normally automatically solve these problems for you. So let's look at a Python function called minimize. All right. So in the real world, obviously, I don't expect you to solve it by hand. Python basically has a minimize function that solve it for you, and all you have to do is put the constraints into the function. Now, a very important key regarding to Python. Remember the standard we have is that g of x has to be less than equal to 0. You always put your function into this format to solve for the KKT condition. Now, different textbooks teach things differently. Other convention is when g of x is greater than 0. We're not going to use that, mathematically speaking. When you're doing it by hand, always do it this way. However, Python uses this convention. Therefore, when you are putting your inequality constraint for Python, you need to put it to be greater than 0. So you got to like switch it around a little bit. All right. So over here, now notice we have x is less than 0, which means x is greater than equal to minus x is greater than equal to 0. So this is the constraint we're going to put. So now we have the objective function, which is x squared, and then the equality constraint h, which is x squared minus x minus 2, right here. That's the equality constraint. And the inequality constraint is minus x, right here. And all you have to do is put it into this constraints. So the first one, h, is the equality constraint. The second one, g, is the inequality constraint. So you put all the constraints together, and then you put the constraints into the constraints for the function minimize. So here's minimize. You're trying to minimize the function objective, and you start at some location. It runs similarly to gradient descent. So you start at some solution, and this will solve it for you, and this gives you the optimal solution. Okay? So this right here is how you can solve with Python. Remember, the solution was -1, right? So that was the solution. All right, pause the video again. See if you can follow this logic and see if you can essentially solve this problem using the 4 KKT conditions. Okay, pause the video. I'm going to go on. By the way, this is the solution. I want you to use Python, by the way. So that was Python. Okay. All right, more practice. These ones, I want you to solve it by hand and then confirm your solution with NumPy. Okay. I have the solutions here for you. Over here, that's the code for it. Over here is the problem 2 solution, the code for problem 2, problem 3 solution, and the code for it. So you can basically look over these. Make sure you know how to do this. This is definitely going to be a problem on the exam. All right, for your last problem, let's say you are a student, you're trying to balance your academic performance versus social life, right? And you're trying to decide how you allocate time efficiently. So we while trying to minimize your stress level. So you're trying to minimize the stress level, which is modeled by this function. So x1 represents how much you study. X2 represents how many hours you spend socializing. If you're trying to maintain the current grade, the student must spend at least 3 times more studying over socializing. So that right there is an inequality constraint. Additionally, to maintain a healthy social life, they need to spend at least 1 hour per week socializing. So that's another inequality constraint, right? Follow through this, write out the KKT conditions, and see if you can solve it. I have the answer. Well, yeah, pause the video. I have the answer here. Um, I think this is it, right? And over here is the code solution. You can look into it. All right, and I think that's it. That's it for today. I will see you in next. I will see you in the next class. Yeah, next class.